So welcome back, everyone. I hope you had a good break. So we are here trying to prove this result, connecting the combinatorial property of a graph being bipartite to the eigenvalues properties of the spectral properties of the adjacency matrix. And so I left you with some exercise that will complete the proof of part one. So there was a question about, we can talk later on in the tutorial about what happens if lambda is 0, if this gives anything, but we can discuss it later. Now let's look at proof 2 and 3, okay? So for the proof of 2, I will use a result that I already used, but I'll state it now more formally. So I will use this fact, proposition, that if we are under the same hypothesis that G is a graph with, gamma is a graph with adjacency matrix A, then the powers of the matrix tell you something about the number of walks in the graph. So you're probably familiar with this. So for any L natural number and any xy vertices, if you take the adjacency matrix and you raise it to the power L and you look at the entry xy, this equals the number of walks of length L from X to Y. Okay, and if you want to add it to the exercises, proof, exercise 10. So prove this. You can use. I'll give you. You can use induction on L to do this. So you take the adjacency matrix. You see, like L is 1. That's the adjacency matrix. A walk of length 1. It's the same thing as an edge. So that's clear from the definition. And then you can use, like I said, induction on L to show that this result. Okay. If you have a walk of length L from X to Y, this is going to be composed of a walk of length L minus 1 from X to some vertex Z and an edge from Z to Y. That's essentially it. Okay. So now let's prove the second part. So 2, assume that gamma is a graph such that the spectrum of A is symmetric with respect to 0. Okay, so I will use a slightly different notation now. So let me put them side by side so that you so the usual notation I use when I don't care about, so this is the spectrum of A. And here I can repeat eigenvalues. That's why I put greater or equal to, okay? Now, if you want to look at the distinct eigenvalues, then I will use a notation more like theta 1 strictly greater than theta 2, strictly greater than, say, than theta t. And then each of them comes with some, so you'll have here, these will be the distinct eigenvalues. And this will be their multiplicities. So it's just a different notation, because if I want to refer to distinct eigenvalues, I'll use the thetas. If I want to refer the whole spectrum, ignoring the repeated eigenvalues, I'll just do lambda. Okay. So let me give you some example. If I have the complete graph K4, then maybe you will have 3 greater or equal to -1, greater or equal to -1, greater or equal to -1. So this is lambda 1, this is lambda 2, this is lambda 3, this is lambda 4. So this one or all equal. If I use the notation, it's just more condensed. You have 3 bigger than -1, and this is multiplicity 1, this is multiplicity 3. So this will be multiplicity 1, multiplicity 2. This will be theta 1, and this will be theta 2, or something. Make sense? This is just a different way of representing the same thing. Okay? Now, I probably don't need it for this part that I will do here, but anyway, I thought I'll introduce it now. Now, for this proof, the key thing is if the spectrum is symmetric with respect to 0, then what happens? Well, in that situation, if I look at, I'll use the thetas. So, because the spectrum of A is symmetric with respect to 0, then if, let's say, theta j is bigger than 0, the multiplicity and let's say the multiplicity of theta j is, let's say, mj, then the multiplicity of minus theta j is also mj. It's the same thing as before, but just stated in terms of theta j's. Okay. And now, what this is helpful? Well, it's what's gonna give us is gonna give us the following. Let's take L natural number or 0. We look at we are gonna look at the trace of a to the power 2l plus 1. We're gonna look at trace of odd powers, and we're going to look at it in two ways. So one way looking at the trace is by eigenvalues. So this is going to be, I'll write it informally here, the sum of eigenvalues. So it's going to be the sum over all j equals 1 to t of, well, let me do it with the lambdas first. The summation from I equals 1 to n lambda I to the power 2l plus 1. And then if you write it with the thetas, it's going to be the summation over j, some j. You will have theta j comes with multiplicity mj, so you'll have something like mj theta j to the power 2l plus 1. But minus theta j, so minus theta j will be an eigenvalue of a. So when you raise a to the power 2l plus 1, minus theta j to the power 2l plus 1 will also be an eigenvalue, and you will have the same multiplicity, so plus mj this. Okay, so this is just a way to show you that in this situation when spectrum is symmetric with respect to 0, if you look at the odd powers of the eigenvalues, you add them up, is going to be 0. That's the whole thing. Okay, so you have trace is this, which is this, and obviously odd powers, they cancel out here, and you will get that this is 0. Now, on the other hand, trace of a of 2 to the l plus 1, you can interpret it combinatorially, and this is a summation over all x in V of a to the 2l plus 1 in the position xx. It's the sum of the entries of the diagonal of the matrix a to the 2l plus 1. But what I just gave you the proposition, what do you count here? Yeah, so it's the total number is the number of closed walks of length 2l plus 1. So this condition about the spectrum, if you go via the trace, it guarantees that the number of closed walks of odd length is going to be 0 for any odd length. So it means you have no odd closed walks. And if you have no odd closed walks, you're not going to have any odd cycles, and your graph is bipartite. That's all. That's all it is here. So I won't write that, but it should be clear for everyone. Okay. So that's the second part. Now there is a little bit of an equivalent characterization. Let me erase it here. I don't know how useful it is, but You can rephrase this condition about being bipartite and spectrum symmetric with respect to 0. You can rephrase it in terms of the coefficients of the characteristic polynomial, on how the characteristic polynomial looks like. So you'll hear more about coefficients of characteristic polynomials from Professor Kanan. I'm not gonna do that here. So this result, so 1 and 2 are equivalent. What I meant to say is that there is an equivalent characterization in terms of the characteristic polynomial of the adjacency matrix of this graph as being some power of x times some polynomial in x squared. But I'll leave it here for now. Yeah.
When we work closed work, I see.
Number of closed. Oh, what is a closed walk?
No. Why we are saying closed work? But a to the power l have the.
It's walk.
What is it?
Yeah, but here it's xx. So it starts at x. So the thing about, you remember, like the thing about walks, like if I have let's say a triangle 1 2 3, I can do 1 2 3 1. It's clear, yeah. So that's, but just to kind of clarify here, like when you count walks, it's kind of like looking at words. So you kind of compare the word how it looks like, even though morally it's the same walk. So for example here, 1 2 3 1, it's a closed walk of length 3. You can have the walk 2, let me go counterclockwise, 2 1 3 1 2. These are considered different walks. So here you count all of them. So you count all of them and you get 0. Okay. Okay, so that's that. Now let's go to 3, because 3 is the more interesting part. So in 3, so you have to be careful about 3. So we have what? Assume you have a connected graph. So we want to prove that gamma is bipartite if and only if this thing happens. Lambda 1 equals minus lambda n, or something. Okay, so one implication is obvious. So from here to here, it's already done. If it's bipartite, we proved here that everything is symmetric, including the largest and smallest eigenvalues. So you're done. The harder part is to go this way. Okay. Now the only thing different from what we did before is that in this situation we assume the graph is connected, and this is a question to. I don't know if this. I don't think this works without the graph being connected. So the graph is connected. So what do we have? So assume that gamma is connected and lambda n equals minus lambda 1. So you don't have the whole information that the whole spectrum is symmetric with respect to 0. Because like in 2. In 2 you have that information, you go to the walks and you're done. Now you only know the smallest eigenvalue is there, you don't know what happens in between. Of course, if you find a way to prove 2, then you're done, but you might as well just go for 1 and so on. So what's going to happen? Now again, I tried to point to you that sometimes the hypothesis, I mean not sometimes, the hypotheses are important in mathematics, so you have to pay attention. And for this part about what we're doing here, when you see connected, it should kind of tell you something about Perron-Frobenius. There's something I need to use about Perron-Frobenius, about the graph being connected. It has to come into play in a certain way. So let's say from Perron-Frobenius theorem, we have AU equals lambda 1 U1 for some U1 in real And u1, let's say we can take it positive, and if you want, you can even take u1 of length 1. Okay. Now this is the thing that we have to use somehow. So we have to go after lambda n, say something about lambda n. Now, what do we know about lambda n? Lambda n is an eigenvalue. Also, let's call this vector un equals lambda n un for some un in Rn, let's say un again non-zero, un of length 1. Now the graph is connected, lambda 1 is bigger than lambda n, they're different. So what thing you know for sure about u1 and un? I didn't prove it, but it may come a bit late. Like if you have eigenvectors corresponding to different eigenvalues, I mean, we took them at the end, it doesn't matter, but so u1 and un are orthogonal, yeah. So, but u1 is all positive. So, because u1 and un are orthogonal, what can we say about un? Un and u1 is positive. Un has positive and negative entries. Okay. And now we're going to write un. How do you want to write un? Un, we write un as follows. So without loss of generality, assume that un looks like this. I'm going to have a v1 on some components, v2 and some components. Okay. So basically I collect here the positive entries, and here I collect whatever is left. Okay, so this is in Rn, where v1, let's say, belongs to some rk, v2 belongs to Rn minus k. Well, I will change the notation. I will make this minus v2. So v1 is positive, so entry-wise, let me put it as vectors. Vectors, vectors, vectors. Okay, so v1 is positive and v2 is greater or equal to 0. Okay, so you can write it like this. And now what do we have? We have that lambda, we have that A times this V1 minus V2 will equal, my eigenvalue is lambda n, but it's the same thing as minus lambda 1. So I'll put it here, okay, I'll put it lambda n first, V1 hat, V2 hat, minus V2 hat, and here it's going to be minus lambda 1, V1 hat minus V2 hat. So this is because of my hypothesis. Lambda 1 is minus lambda 1, isn't it? Now, because I have this multiplication here with this kind of block vector, I can think of A being partitioned according to the partition of V1 and V2. So if V1 is dimension k and V2 is dimension n minus k, B is going to be the first k by k, and this is going to be the remaining n minus k, n minus k. So if you want kind of an idea, okay, what is the guiding idea here? You want to show that your graph is bipartite. You want to go after you want to find a partition of the vertex set such that the matrix is going to be 0, something, transpose of something, another 0. So our goal now is to try to get rid of the B and the E and try to prove that B and E. If we can prove, so clearly C and D are going to be the transpose of each other, but just leave it like that for now. And if I can prove that B and E are 0, then the adjacency matrix will be a block of 0, something. This will be has to be transpose of something, and this has to be 0. Okay? So for now, you kind of do some algebra and you expand this. So if you do the calculation here, I'll start from the right. You get minus lambda 1 V1 equals B. So this is minus, sorry, is B V1 minus C V2. And then the other one is going to be lambda 2 V2 is going to be D V1 minus E V2. Lambda 1, thank you. Okay. Good. Okay, so that's one thing. The other thing is we can get our hands on lambda, minus lambda 1 from here. Remember, like this vector v1, v2 is unit. And if I want to get just this number, I can multiply to the left by the transpose of this vector, like this really business, quotient business. So we multiply from this equation here, I multiply to the left by v1 transpose minus v2 transpose times this matrix B, C, D, E minus v2. Here it's going to be from the left v1 transpose minus v2 transpose minus lambda 1 and this with this gives me 1, so it's minus lambda 1. Okay. And now there's some algebra, but you kind of have to do it. I'm sorry. It's for an afternoon. We have to do some algebra. It's v1 transpose minus v2 transpose meets, what do I have here? B v1 minus C v2 d v1 minus E v2 equals minus lambda 1. And one more, this is transpose, this is transpose, this is transpose. So it will be v1 transpose B v1 minus v1 transpose C v2. So I take this, I multiply here, and now I have to take this minus v2 transpose d v1 plus v2 transpose e v2 minus lambda. I hope I didn't make any mistakes. Okay. Okay. So the last one for now, I want to get to lambda 1, so I just change the sign. So I'll get lambda 1 here, and I just change the sign, so it's minus v1 transpose B v1 plus v1 transpose C v2 plus v2 transpose D v1 plus v2 transpose E v2. Okay. So you get, after all this work, you end up with something like this. Okay, question?
the last one should be minus V2 transpose.
Yes, thank you. Okay. All right, but there's one thing that we haven't used. We haven't used lambda 1 is the largest eigenvalue. So let me erase here. So again, remember, like we started with this vector v for lambda n, which has this partition v1 minus v2. Okay. So now what we're going to do is we're going to do something. We will say lambda 1. Remember, lambda 1 is the max of all W transpose A W over all W of length 1. He beats everybody, okay? So I will take a vector. This vector v1 minus v2 has length 1, but this is the vector of lambda n, so I won't get anything from it. But I will take the vector v1 v2, which also has length 1. So again, this vector, you see, so v1 minus v2, this is the one for lambda n. Now, if I take the vector v1 v2, this is, I don't know if this is an eigenvector for lambda 1. I don't know and I don't care, but for sure I know that this one has length 1 because the length of this vector, it's the same as the length of this vector, and I picked this to be length 1. And from this characterization of lambda 1, I know for sure that lambda is going to beat what? Is going to beat this transpose A v1 v2. So now we just have to do the calculation. So lambda 1 is going to be greater than. We've already done the calculation, so let's just do it again. So this one comes with a transpose. It will be easier now because everything is with plus. And now you don't need to worry about it's. I think it's going to be something like this: v1 transpose b v1 plus v1 transpose c v2 plus v2 transpose d. Let me see. dv1 plus v2 transpose e v2. Okay, so now look at this and look at this. What do you see in common? You see a lambda 1 here. Lambda 1 actually equals this. And you see a couple of terms in common. So the diagonal, the diagonal terms, well, not the diagonal, the other one. This is a minus, sorry. This is a minus. The off-diagonal one. So this one and this one are in both. This one has them with negative. So if I look at this expression and I look at that expression on the left-hand side, which one is bigger? This one here. So this is greater or equal than minus v1 transpose b v1 plus v1 transpose c v2 plus v2 transpose d v1 minus v2 transpose e v2. And from the calculation, so I got this calculation from the hypothesis lambda n is minus lambda 1. I know that this equals lambda 1. Okay, lambda 1 greater or equal than this. Greater. Why do you have greater or equal here? Because v1, v2 are positive, and the matrix B and C are non-negative. So clearly this beats it. It's good. So lambda 1 greater or equal to lambda 1. Therefore, equality everywhere. How can you have equality? Okay, I must have equality here. I'll leave that alone for now. I don't know, I'll get something. Essentially, this will be an eigenvector for lambda 1, but I don't care. But you have equality here. So if you have equality here, what must happen? This thing has to equal this thing, and this thing has to equal, so this and this, and this and this. Because these are the two terms that are different, so they have to be equal. So how can they be equal? The matrix B, because again, what you're using that V1 is positive. So what happens is that this B and the E have to be 0, and they disappear here, and you're bipartite. Okay, so this is one proof of this fact. There is another proof where you can look at the powers of the adjacency matrix, but that proof uses the real Perron-Frobenius theorem for matrices and so on, for irreducible matrices. So I'm not going to do that here, but this is the proof that you can do. So I was talking to some of you during the break. You have to be careful, because it's easy to, like we're always kind of tempted to get the, like one quick characterization for a certain property. So a bipartite spectrum symmetric to respect to 0. And then you remember, okay, if the largest eigenvalue, if the smallest eigenvalue equals the negative of the largest eigenvalue, then the graph is also bipartite. But you have to remember the hypothesis of being connected. So if somebody tells you, I have a graph that has largest eigenvalue 3 and smallest eigenvalue -3, and your friend is telling you, oh, therefore it's bipartite, you have to argue with your friend a little bit. You know what I mean? We all have to do that sometimes. So you need to be connected for that part. So tomorrow I will show you another example when we talk about interlacing. When we talk about Cauchy interlacing, there is a place where we'll talk about eigenvalues of a subgraph induce eigenvalues of the big graph. Interlace the eigenvalues of the big graph. But it's always eigenvalues of an induced subgraph interlace the eigenvalues of the big graph. So the subgraph has to be induced. So you have to pay attention to these details a little bit. Okay. All right. So this is the proof. Any questions? No. Okay. Let me see if I had anything else to show them. I didn't, so we can do some exercises, maybe, or, yeah? I don't know the count. What exercise are we? Yes, you have a question?
We have to show that C equals to D transpose.
No, because C equals to D transpose, you get it automatically. Because when you start with your adjacency matrix, because you have this partition of V1, V2, you say, okay, I'm going to call this block B, this is C, this is D, this is E. So this is K by K. And now what do you know about A? Symmetric. So because it's symmetric, C and D are transposed. Like, I didn't, I didn't bother to call, I should have called this C transpose, but transpose is going to mess it up. So B, C, D, it's a bit easier. Okay? Thank you. Yeah, good? Okay.
So
yeah, you have a question? Yeah.
I know some different proof. It's relatively easier than this. Maybe.
Yeah. You can show, like Professor Karan can show you a proof.
Not my proof.
Do you need a microphone?
No, it's okay.
No. He has microphone.
Contains some mistake, please be careful about it. So lambda, this is, so if un is the least eigenvector corresponding to the least eigenvalue, then we have this. So you define now, you consider this absolute value vector. So this I can draw. Right? So this is the Rayleigh quotient of this vector. Okay? So lambda 1 is the largest one. So this should be less than or equal to lambda 1. By hypothesis, we have lambda 1 equal to absolute value of lambda n. So everywhere you should have equality. And in one of the exercises you have, if lambda 1 is equal to this thing, then that should be the eigenvector corresponding to lambda 1. Yeah. So, okay, so you have A now un is orthogonal to the parent vector, so it should have both the positive and negative entries, or otherwise lambda n is strictly negative since G is connected. A is a non-negative matrix, so un should have both positive and negative entries. Okay, so here you have equality, so that means that everywhere you should have inequality. From here to here equality, when you will get all terms should be the same size, same sign. Okay, so that means that un into unx into uny should have same sign. Same sign or every term inside should have negative. Okay, same sign, negative. From here to here, if I should have equality, then un into unx into uny, they should have the same sign. This product should have the same sign. That means negative, because un already has one positive and one negative entry. Okay, so that means that everything should be negative here. So whenever I have an edge x between x and y, one end should be positive, the other end should be negative. That gives you the bipartition. So collect V1, this is set of all x such that u and x is strictly greater than 0, and V2 is set of all x such that, or y such that u and y is strictly less than 0. Okay, if you almost have y, un should contain only positive and negative entries, it may contain 0. That cannot be, because absolute value of un, this is giving you the parent vector. The parent vector should consist of all positive entries. So this is the, okay. So V1, V2 gives you the bipartition.
What is the definition of parent vector?
Parent vector is the eigenvector corresponding to the largest eigenvalue. This is.
We're just using So where we are using connectedness, where we are using?
So existence of this positive vector, the third point in the morning service lecture, you have a positive eigenvector which has multiplicity equal to 1. Okay. Is it clear?
So his argument shows that absolute value of un is an eigenvector for lambda 1.
See, this is a set of real numbers and this is a set of real numbers. So I'm taking the absolute value, I'm claiming that I'm getting equality here. So when we'll get equality? No, inside the sum, whatever you have, everything should have same sign.
Connectedness, where we are using?
Everything should be negative or everything should be positive. When everything will be, everything cannot be positive, because the vector un is orthogonal to u1. Or in other words, easily, lambda n is strictly less than 0. We are considering this part. Un transpose A un. A is a non-negative matrix, 0, 1 matrix. So if every entry of un is non-negative, then you are going to get lambda n as a non-negative quantity. That's not the case. So un should have negative entries. Okay, that forces that whatever the same sign we are expecting, the sign should be negative. That is, whenever u and x is positive, u and y should be negative.
You guarantee that the smallest eigenvalue.
So
the eigenvector
collect
is perpendicular on
the vertices x and y according to their sign. That will give you the bipartition. So whenever you have an edge, one end should be in V1, the other end should be in V2. And you can't have an edge from V1 to itself, because if you have an edge from V1 to itself,
an eigenvector
that xu into unx into uny corresponding to that one, you will get
I
positive.
took an eigenvector for lambda n, which is perpendicular to that. And
The idea morning
because
Sebi
because
explained,
the first
just
eigenvector is
only the last
positive,
part we can.
It means that the one of lambda n has to have positive and has to have some non.
In doubt?
So that's why I could partition into V1, V2.
This is not my idea.
minus V2.
Yeah, I found it in some place when I was teaching this course. I gave this proof.
Huh?
Connected.
No, it's because of Perron-Frobenius.
Parent Frobenius, because of the
Because the graph is connected, implies that U1 is positive, therefore U1 and perpendicular to it is going to have positive and non-positive entries.
okay.
So we are just using the fact of Perron-Frobenius.
Yeah, just the fact that you have a positive eigenvector for the first eigenvalue.
That I am understanding, but I am not able to see that connectedness of the graph.
In the proof.
So you get positive eigenvector from the connectivity
Okay,
of
that's
the graph in Perron-Frobenius. Yeah. Okay. Oh, sorry.
Okay. Now
Okay.
we need some volunteers for start solving the math.
So I understood there should either be both positive or both negative whenever there is an edge.
Yes.
And then once we conclude this is a bipartition.
See, what is the sum says? Whenever I have an edge
Yeah.
between x and y, at that time only I will have some non-zero terms here.
Yeah.
Okay. So if we have an edge from V1 to itself, then that means that both ends are having positive.
Oh, okay.
Or
Yeah,
it will
you
be
just
positive.
define this and
Uh-huh.
observe that this is a
So bipartition. Yes. Okay, so maybe you can volunteer for solving problems one by one. The initial problems are easy.
Oh, maybe do I have to call on people?
Yes, sure.
Yeah, we have 15 minutes or 20 minutes. Okay. I lost track of exercises. Anybody remember? Oh, no.
Abhay is typing.
Oh, okay.
Some of them are already.
Okay. Okay, so let's do the exercise question 10. You have this thing with the bipartite, so it looks like this. And we said something that if you have, you have these vectors u1, v1, so this was the first part. This, and how did we, what was the argument here? Where were we using this? This was a basis for, remember, fancy E lambda. And we proved that this is, these are eigenvectors of minus lambda. So if we prove A, we get that the multiplicity of lambda, we get the multiplicity of minus lambda is going to be greater or equal than multiplicity of lambda. Because multiplicity of lambda, we take m, and I have a basis here, and it's linearly independent, then it guarantees that these things are going, because these ones we already proved that they are eigenvectors for minus lambda. So once you prove multiplicity minus lambda is bigger than lambda, you can do the same argument for minus lambda and lambda, and you get that they're equal, okay? So clearly A implies B, but A requires, is it obvious? Or? So I'll let you think for 2 minutes. I'll erase the board, and then somebody can come and write down a proof. Wow. I told them 2 minutes, so give them 2 minutes. Yeah.
If someone likes your presentation, they may give you job immediately.
Yes.
Positive.
Okay, I don't know what to do. Should I keep asking them, or are they, or should I talk about something else? We'll leave it.
Anybody got the answer?
Okay, do you want to go write it down for everybody? Come on, it's okay.
Some of them they vote.
Yeah.
So we can assume it as LD, then it would be like alpha 1 and let it as x1. From here it will be alpha 1 and from the second this will be alpha 1 beta. So if it is LD, then at least one of them must be LD. This one or that one. Okay. So if any one of them is LD, so okay. So this is a line. So from here it would be alpha 1 u1, alpha and u1 equal to 0, and alpha 1 u1, alpha and u1 equal to 0. This implies alpha is need to be equal to for all. So if it is Li, means if we take any linear combination of these vectors, then all alpha must be equal to 0. But I am taking here it as LD, and if it is LD, then it means this or this alpha must be non-zero. So from here alpha I must be 0, and here we are getting alpha I as non-zero. Contradiction.
Any questions? Clear? So I think you're proving the contrapositive, just linear dependent implies linear dependent. Yeah, yeah.
So if it is LD, then it means it should also be.
Yeah. And yeah, this is useful because it gives you a recipe. If you know some eigenvectors for an eigenvalue for bipartite graphs, you can get the other ones just by changing the sign. Yeah, very good. Okay, all right, thank you. Okay. Very good. Very good. Okay, so I was looking at the schedule, so we're supposed to do in lecture 2, I guess I didn't have time, Rayleigh quotient, max-min theorem, and so on, and so maybe I'll do that now.
The break shall we do?
You do break now? Oh yeah, let's do break and then I'll do this. Okay, we'll take a break now.
Maybe some type problems you can do. Calculating eigenvalues of complete graph. Specifically, I think some of.
Yeah, I gave them the. Did anybody do the orthonormal basis of Kn? Or okay, so where are we with exercises? Number 11. Okay, exercise 11. Okay, before I give you exercise 11, let's do some, okay, so complete graph Kn, adjacency matrix of Kn is Jn minus In. Eigenvalues, I'll give you another n minus 1 with, I'll put it multiplicities as exponents, 1, and minus 1 with multiplicity n minus 1. So this is the same kind of notation as before, but multiplicity as exponents. The second one, complete graph KAB, complete bipartite KAB, adjacency matrix of KAB is 0A, all 1AB, all 1BA, 0B, and then find eigenvalues, square root of AB with multiplicity 1, 0 with multiplicity L plus B, A plus B minus 2, and minus square root of AB with multiplicity 1. Okay, so I haven't done the proofs of this, but you should know how to do if somebody, you know, asks you how to calculate. This one is pretty straightforward. This one is a little bit of work, but it's not complicated. So here again, find for Kn and KAB. Let's see how, if you want to do it by hand, how complicated it is. So you can have fun with it. Then we can, if you want, we can take a break now.
Yeah.
Yeah. Okay.